unnoticed, she knows no limit, she craves attention, she praises an image she prays to be sculpted by the sculptor. Oh, she don't see the light that's shining deeper than the eyes can find it. Maybe we're made of blind souls. She tries to cover up her pain and cut her woes away. 'Cause cover girls don't cry after their face is made.
Hello, boys and girls. It's Mr. Landry again, and we're going to continue today with our study of logarithms. Okay. Last time I asked you to think about when, if the directions say multiply, do you add? And when, if the directions say divide, do you subtract? Well, if you guys thought of the word exponent, you were correct. Logarithms are exponents. That's how Sir John Napier got rid of multiplication and division and made everything addition and subtraction by working with logarithms. The word logarithm is just a fancy word that means exponent. It's a word that was coined by Sir John Napier. The rhythm part probably comes from arithmetic, log meaning word, but logs are exponents. When you see the word log, I want you to think exponents. We're much better thinking in exponents. Just like if somebody comes from Europe and tells me they're a size 42 shoe, I can't envision that. Okay? Because it's the metric system. I'm used to the English system. So when we see the word logs, we're going to change them to exponents because they are basically the same thing. Because you guys have been studying exponents since probably the 4th grade, so you're good with it. But logarithms are exponents. And if you think about it, if I gave you 10 to the 3rd, and you multiplied it by 10 to the 5th, you wouldn't do any multiplication. You would simply say, same base, add the exponents, 10 to the 8th. When we are multiplying, we add exponents. Well, then we'd add logs. When we're multiplying, we add logarithms. And if I gave you 10 to the 9th, divided by 10 to the 7th, you wouldn't actually do any division. You would just say, oh, it's 10 to the top exponent minus the bottom, 10 to the 9 minus 7, or 10 squared. When we divide, we subtract exponents. Therefore, we subtract logs. Logs are exponents. And what we're going to do today is talk about what we call simple log equations. Simple log equation is an equation where the word log appears only once. That's what I call a simple log equation. There's a simple log equation. It's an equation. Word log appears once. Well, let me show you what this says. This says the exponent of 10 is 2. The word log means exponent. The exponent of 10 is 2. The exponent of 10 to get 100 is 2. The exponent of 10 to get 100 is 2. I'm going to rewrite this. The exponent of 10 is 2, and it gives you 100. Kids, this is going to be your Rosetta Stone. You memorize these two things together. And just like the Rosetta Stone helped them translate Egyptian hieroglyphics, well, this is going to decipher logs for you. These two equations say the same thing. Both of them say 10 to the 2nd power is 100. Exponent of 10 is 2. We're going to use that. Anytime we have a simple log equation, we're going to change it to an exponent because we can think in exponents. Let's look at a couple of examples. I put my Rosetta Stone here on the side. Here's a simple log equation. I'm going to solve it now. Okay? It's a simple log equation, has an equal sign, makes it an equation, word log appears once. And feel free to stop the video if you want to try it first before you see how it's done. Okay? I'm going to change this to an exponent equation. This little number, the base, becomes the big number. There's the exponent, and it's equal to 49. Just like the little 10 became the big 10, well, the little x becomes a big X. The exponent is on the other side. See, logs make exponents the most important thing. See, the exponent has its own side. And now it's an exponential equation. You guys can do that in your head. Something squared is 49. 7. Yes, it's also -7, but let's talk about that in another lesson. Let's leave it as 7 for now. Okay, let's try another. Log base 2 x equals 4. Simple log equation. An equation, word log appears once. Let's change it to an exponent equation. The little number becomes the big number. There's the exponent on its own side, and it's equal to x. There you go. X is 2 to the 4th. You want to leave it like that, it's fine. You want to change it, figure out what 2 to the 4th is, it's 16. That's fine also. There you go. Okay. Take a simple log equation, change it to an exponential equation. Try another. Simple log equation. Equation, word log appears once. Little number becomes the big number. There's the exponent on its own side, equals 81. The exponent of 3 is x. And I'll have to sit for a second, think about that. 3 to the 1st, no, that's 3. 3 squared, 3 times 3, 9. Now, 3 to the 4th is 81. Three times 3 times 3 times 3. Okay. Let's try another. Simple log equation. The word log appears once. Now some of you might say, wait, something's missing here. There's no base. There's no little number. Well, kids, when you have the word log, if there's no little number, it's understood to be 10. If you have the word log, L-O-G, and there's no little number, it's understood to be 10. These two equations say the same thing. These are called base 10 logs or common logs, C-O-M-M-O-N. These were the logs that Sir John Napier worked with and Henry Briggs back then. Okay, base 10 logarithms, common logs. Now, let's change it to an exponent equation. It's a simple log equation. The little number becomes the big number. Exponent is over there, and it's equal to 1,000. 10 to what power is 1,000? 10 times 10 times 10. 10 to the 3rd. There you go. So, guys, if the word log appears, L-O-G, and there's no little number there, no base, it's a 10. Okay. Let's look at another. Simple log equation. Equation, word log appears once. Change it to exponents. The little number becomes the big number. There's your exponent all by itself, and it's equal to x. Oh, a negative exponent. We don't like to leave things with negative exponents. Now, if you've forgotten, you want to make a negative exponent a positive exponent, make a fraction, and put that thing on the bottom, and it becomes a positive exponent. Put whatever has the negative exponent on the bottom of the fraction, and it will become a positive exponent. If it's already on the bottom, put it on the top. Nothing's left up there, put a 1. 1 over 3 squared, or 1/9 is x. Don't get nervous if you see negative exponents. It just means put them on the bottom and they become positive. Here. Here's another. 2 to the negative 3. Well, you don't want a negative exponent. Take the thing that has the negative exponent, put it on the bottom of a fraction, and it becomes a positive exponent. It's 2 to the 3rd. Nothing up there, put a 1. 1/8. 2 to the negative 3 is a fancy way of writing 1/8. Okay. All right, let's look at our next one. Simple log equation. Okay. The little number, and again, feel free to stop the video if you want to try it first. Little number becomes the big number. There's the exponent on the other side, and that's equal to x. Oh, a fractional exponent, an exponent that's a fraction. Well, if you forgot about those, whenever you see a fractional exponent, make a root sign. Put the number in the root. The bottom of the fraction goes in here. And the top of the fraction stays up top. See? 81 to the 1/2. That's the square root of 81. Square root of 81 to the first power, which is 9. That's how you handle fractional exponents. Make a root sign. Do another just so you feel confident with it. Let's say they give you 8 to the 2/3 and you want to find out what that really is. You see a fractional exponent, make a root sign. Put the number in the root sign. The bottom number goes in the sleeve and the top number stays up top. 8 to the 2/3 power. Well, cubed root of 8. What times what is 8? 2 to the second power, or 4. 8 to the 2/3 is a fancy way of writing 4. Okay. And let's try one last one. Simple log equation, where log appears once. Okay. However, that's not LOG, that's LN. Kids, when you see LN, that's called the natural log. See, LOG is the common log, base 10. If there's not going to be a little number there, we understand it to be base E, a lowercase e. These two equations say the same thing. When you see ln, it's a natural log, the base is e. That e is called the Euler constant, E-U-L-E-R. It's named after the famous Swiss mathematician Leonhard Euler. Don't ask me why that's pronounced Euler. He lived from 1707, 1783. It's a transcendental number. It's like pi. You know how you all know that pi is 3.14? And anytime you take the circumference of a circle and divide it by the diameter, you get pi. Well, the Euler constant is a number that occurs all the time in non-linear growth. Non-linear growth would be like mitosis. You know, you have one cell, undergoes mitosis, becomes 2. Then it undergoes mitosis again, becomes 4. That's non-linear growth. Like this current COVID virus is non-linear growth. One person generally infects 3. Well, the Euler constant is non-linear growth. It occurs, it's the number 2.71 with a zillion decimals. That's what E is, okay? You'll study it later. But let's get back to the equation. It's a natural log. The little number becomes the big number. There's the exponent. And it's equal to x. You want to see what E is? Okay. The E is on top of your division sign. Second E. See, it's right there on top of the division sign. And I want it to the 4th power, 54.598. But I'll tell you a little secret. You could have left it like that also. They accept e to the 4th just like they accept pi. All right, I'm going to stop there. I'll leave you with a song by Betty Wright, a very great singer who passed away today. This song was very popular when I was studying logs back in the early 70s. Okay, and I'll see you kids tomorrow. Take care, be safe.